here, what I'm going to do is I'm going to show you the process by which you go from the weak form to a set of algebraic equations. And it's really the heart of the finite element method. And I didn't understand this for the longest time. I'm trained in CFD and in fluid dynamics and in the finite difference method, which is actually not used very much in industrial codes. And so what I did was, to understand this process of going from the weak form to the algebraic equations in the finite element method, I just shut the textbook. And I said, I'm just going to work it out myself. And in the process, I begin to understand, oh, these are the tricks that are happening. And then now when I'm in ansys, I'm using these insights all the time. So I'm going to share those insights with you. And I'm trying to do this very, graphically, because usually it's presented this as with a lot of algebraic a lot of equations and so on, which really I think takes away from the understanding. Okay, so we have our weak form, which is over here, and we have our domain divided into 3 elements. So you can think of each element as a segment of the domain. And we have the assumed shapes for the temperature and for the weighting function. And we want to satisfy this equation for these shapes. And when I do this integration, and I'll do this integration element by element. So when I do the integration over the first element, I'll get terms where I'll have W1 multiplying T1, and I'll also get a term where W1 multiplies T2. Okay, so I'll get a term that involves W1 times T2 and W1 times T1. And you have some, constant coefficients here which you have to work out. It's going to depend on K, and it's going to depend on this element length. We won't worry about what that constant coefficient is. And interestingly, when you go and do the integration over the second element, you won't get any terms involving W1. Okay, so those are the only 2 terms where you get W1 multiplying a nodal temperature. Then when I go to let's consider W2. So you'll get a term, when you do the integration over the first element, you will get a term where W2 multiplies T1. So you'll get a term like that. You will also get a term where W2 multiplies T2. And then when you do the integration over the second element, you will get W2 multiplying T2, so that you can clump in over here. And then you'll get W2 multiplying T3. Okay? But you won't get any terms where W2 is multiplying T4. So you see these terms, W's will multiply only the neighboring nodal temperatures. And then it's like you get all these terms and you put them all together and you organize them in a particular way. And I've done that here. And I'll unpack this. Okay, so this is a lot of terms. So let's look at the first row here. What I've done is I've shown you if you take all the terms that are multiplying W1 and you organize them like this is what you'll get. Okay, W1 will multiply T1, you'll get some constant coefficient here, it'll multiply T2, it'll multiply, so you'll get a term involving W1 from here. So that's that term here. And then this term is from here. So this term comes from there. And similarly for W2. So at W2 you will get terms where it's multiplying T1, T2, T3 as we talked about. And then you will get a term from there. So from the heat generation term, which is called a source term. But you won't get anything from this one. Okay, so this term affects only, this gradient term at the boundaries will affect only the nodes at the boundaries. So since 2 is not at the boundaries, you don't get that term here. And similarly for W3 and W4, that's equal to 0. Now we are trying to satisfy this for arbitrary W, which means that our nodal values here, these are arbitrary. So if you want to satisfy, this to be equal to 0 for any values of W1, W2, W3, W4, the only way you can do this is each individual term is equal to 0. So which means since W1 is arbitrary, I will set that as equal to 0. And that gives my equation at the first node. So whatever multiplies W1, these terms will contribute to the equation at the first node. Whatever multiplies W2 will contribute to the equation at the second node, and so on. And so that's the process by which you go from the weak form to the algebraic form. And it's also, useful to, as a code user, it's also useful to know how each of these terms, where it goes in the algebraic equations. And we'll use those insights when we are in ansys. So that's what we'll look at next.